We've all looked at the stars and asked the same question. Is anyone out there? But what if the answer just arrived? And it's a million times weirder and more incredible than we ever imagined. The James Webb Space Telescope just saw something 120 light-years away that is off the charts. It's a planet with a perfect 120-degree Fahrenheit temperature and a chemical signature that is a straight-up neon sign for life. It's a 99.7% certainty. We found it. This isn't a myth, a maybe, or a theory. It's not a myth now. The secrets of distant worlds often arrive not with a bang, but with the quiet hum of data flowing into a computer. On a seemingly ordinary Tuesday morning, nestled within terabytes of infrared light meticulously captured by the James Webb Space Telescope, lay a revelation that would shake the foundations of our understanding of life in the universe. This wasn't a message etched in radio waves or a colossal structure observed in space. It was far more subtle, far more profound. A chemical whisper carried across 120 light-years from a planet residing in the constellation Leo. At Cambridge University, astronomer Niku Madhusudan and his team were engaged in the painstaking work of analyzing the atmospheric compositions of exoplanets, worlds orbiting stars beyond our solar system. Their focus turned to a specific world designated K2-18b, a planet that had already hinted at intriguing possibilities due to its location within the habitable zone of its red dwarf star. The habitable zone, often dubbed the Goldilocks zone, is the orbital region around a star where temperatures could allow for liquid water to exist on a planet's surface, a key ingredient as we currently understand life. The James Webb Space Telescope, with its revolutionary ability to observe the cosmos in infrared light, provided an unprecedented opportunity to scrutinize the light that had filtered through K2-18b's atmosphere as the planet passed in front of its star. This technique, known as transit spectroscopy, allows scientists to decipher the chemical makeup of a distant world's atmosphere by analyzing the specific wavelengths of starlight that are absorbed or altered by the gases present. Infrared light is particularly crucial for this endeavor because many molecules, especially those indicative of life, have unique absorption signatures in this part of the electromagnetic spectrum. As Madhusudan's team meticulously examined the spectrum of light from K2-18b, a particular set of wavelengths screamed out, forming a pattern that should not have been there according to conventional astrochemical models. There, amidst the expected signatures of water vapor, methane, and carbon dioxide, was the unmistakable fingerprint of dimethyl sulfide, or DMS. This relatively simple molecule, composed of sulfur atoms bonded to methyl groups, holds an extraordinary significance in the search for life, because on Earth, it is produced almost exclusively by biological activity. The vast majority of DMS in Earth's atmosphere originates from phytoplankton, microscopic marine algae that form the base of many aquatic food webs. As these organisms metabolize and break down, they release DMS as a byproduct. What made this detection so compelling was not just the presence of DMS, but the strength of the signal. It wasn't a fleeting trace amount that could easily be dismissed as noise or contamination. Instead, it was a robust and clear signature, so much so that rigorous statistical analysis revealed an astoundingly low probability of it being a false positive, less than 3 in 1,000. This translates to a 99.7% confidence level, a threshold rarely reached in the complex and often uncertain field of exoplanet atmospheric studies. For context, such a level of certainty is akin to the standards used in particle physics to announce the discovery of new subatomic particles. For scientists who have dedicated their lives to the search for life beyond Earth, this moment was transformative. It wasn't just another intriguing anomaly or a promising hint. It was the closest we have ever come to direct evidence that we are not alone in the vast expanse of the cosmos. The detection of dimethyl sulfide in the atmosphere of K2-18b is not merely an interesting chemical curiosity, it is a potential biosignature, a telltale sign that a distant world is in some way alive. This discovery compels us to look beyond Earth-centric notions of habitability and to consider the possibility that life can flourish in environments dramatically different from our own. The journey to understanding this alien world and the life it may harbor has just begun. The world that holds this incredible secret is a planet unlike anything in our own solar system. Designated K2-18b, it belongs to a class of planets that astronomers call super-Earths, or, more accurately in this case, mini-Neptunes. This is a category of worlds that are bigger than Earth but smaller than Neptune, and until recently scientists believed they were hostile, uninhabitable gas balls. K2-18b has forced a complete and total re-evaluation of that assumption. To put its size in perspective, K2-18b is a colossal world. It boasts a radius of about 2.6 times that of Earth and a staggering mass of approximately 8.6 times our planet's. On the surface of this world, the gravitational pull would be nearly 3 times stronger than what we experience on Earth. A person weighing 150 pounds here would feel the equivalent of over 400 pounds on K2-18b. Yet, as we will discover, this immense gravity is not a disadvantage for life, it's a crucial advantage that acts as a powerful shield. The planet's density, or the amount of matter packed into its volume, is another key piece of the puzzle. At 2.67 grams per cubic centimeter, its density sits squarely between that of Earth's rocky core and Neptune's gaseous nature. This unique density tells us a profound story about its composition. It's not a purely rocky world like our own, nor is it a gas giant. Instead, computer models and the latest data from the James Webb Space Telescope suggest that K2-18b is a Hycean world, a portmanteau of hydrogen and ocean. It's believed to have a rocky silicate core encased in an immense mantle of high-pressure water, which is then enveloped by a thick, hydrogen-rich atmosphere. It is a true water world, but on a scale and with a chemical makeup that is completely alien to us. The planet's orbit around its small red dwarf star takes just 33 Earth days, making its year incredibly short. This close proximity, however, does not make it a scorched wasteland. Because its star is so much cooler than our Sun, this short orbit places K2-18b perfectly within its star's habitable zone. It receives almost the exact same amount of energy from its Sun as Earth receives from ours. This cosmic coincidence makes it a perfectly temperate world, but with one major difference. It is almost certainly tidally locked, meaning one side of the planet is forever facing its star in a state of perpetual daylight, while the other side is locked in an eternal freezing night. This unique rotation creates an environment of extremes that would shape any life that might exist there in ways we can only begin to imagine.
While the sheer scale of K2-18b is impressive, its most profound secret is not in its mass, but in the air that blankets its surface. The atmospheric chemistry of this world reads like a page from science fiction, yet the data is as real as it gets. On Earth, we live and breathe in a thin envelope dominated by nitrogen and oxygen. On K2-18b, the atmosphere is a completely different beast, a dense, thick, and suffocating layer of hydrogen and helium. These are the same elements that make up most of the universe, and their presence here creates an environment that defies everything we thought we knew about planetary habitability. This hydrogen atmosphere isn't just a simple collection of gases, it is the planet's life support system. It acts like a massive planetary blanket, a perfect insulator that traps heat with incredible efficiency. This creates what scientists call a runaway greenhouse effect, but in reverse. On Venus, carbon dioxide creates a greenhouse effect that cooks the planet into a molten hellscape. On K2-18b, the hydrogen acts as a perfect insulator, maintaining a stable temperature of 120 degrees Fahrenheit across the entire globe. This temperature is not just habitable, it's remarkably stable, a planetary thermostat perfectly calibrated for life to exist. This thick envelope of hydrogen also plays a crucial role in creating the conditions for liquid water to exist. Unlike Earth, where temperature variations between day and night, summer and winter, create complex weather and climate zones, K2-18b's dense atmosphere redistributes heat so efficiently that the entire planet maintains a consistent, life-friendly temperature. This means that liquid water, a fundamental ingredient for life as we know it, could exist everywhere, from the perpetual day side to the eternal night side. The thick atmosphere also protects any potential life from the intense stellar flares emitted by the red dwarf star, which would otherwise be lethal to life on the surface. This is the very essence of a Hycean world, a planet with a massive, life-sustaining ocean beneath a hydrogen-rich atmosphere. The atmospheric chemistry isn't just a static mixture of gases. It's an active player in creating an environment that is not just possible for life, but potentially more hospitable than our own. It forces us to reconsider the most fundamental question of all. Is Earth's atmospheric chemistry the only way for life to thrive? The answer from K2-18b seems to be a resounding no. And it is this very atmosphere that contains the next profound clue in our search for life.
The story of K2-18b is inseparable from the story of its star. While the planet is a true marvel, it is the star that provides the foundation for its existence. K2-18 is not a star like our Sun. It is a red dwarf, a type of star that is smaller, cooler, and dimmer than the one that warms our world. If you were to stand on K2-18b's surface, its star would appear as a large, deep red orb in the sky, not the brilliant yellow-white beacon we see from Earth. But this unassuming red dwarf is, in many ways, a far more effective engine for life than our Sun. Red dwarfs are the most common stars in the Milky Way, making up about 75% of the galaxy's stellar population. They burn their nuclear fuel so slowly that they can maintain a steady energy output for trillions of years, a timescale that dwarfs the entire current age of our universe. Our Sun, by comparison, has a lifespan of about 10 billion years. This incredible longevity has profound implications for life on K2-18b. On Earth, it took nearly 4 billion years for complex, multicellular life to evolve from simple bacteria. On K2-18b, with trillions of years of stable energy at its disposal, life could have had an almost unlimited amount of time to develop complexity that is beyond our imagination. This long-term stability is crucial. Unlike our Sun, which will eventually expand into a red giant and incinerate our planet, K2-18 will continue to shine steadily for an unimaginable amount of time. Any life that evolved on K2-18b would have a permanent, reliable source of energy for an era longer than the universe has yet existed. This, combined with the planet's tidally locked rotation, creates a world of unique extremes. One side is bathed in perpetual twilight, forever facing the star, while the other side is locked in eternal darkness and cold. This might seem like a disadvantage, but K2-18b's incredibly thick atmosphere efficiently redistributes the heat, making both sides potentially habitable and stable for life to explore and exploit. The story of K2-18b and the life it may harbor is a testament to the immense power of its star and the incredible resilience of its atmosphere. But none of it would be known to us without the one tool that made the impossible a reality: the James Webb Telescope. Webb is not just an ordinary telescope. It is a technological marvel floating 1 million miles from Earth at a stable gravitational point known as L2.
At this location, it exists in a state of perpetual darkness with a massive sun shield the size of a tennis court blocking all light and heat from our star. This allows Webb's instruments to remain colder than the surface of Pluto, a crucial condition for it to function. To understand why this extreme cold is necessary, we must understand the mission of the telescope. While the Hubble Space Telescope gave us stunning visible light images of the cosmos, Webb was built for a different purpose: to see the universe in infrared light. Infrared is invisible to the human eye, but it is the key to detecting life on distant worlds. Everything in the universe, from stars to planets to human bodies, emits infrared light, which we experience as heat. Webb's instruments are so sensitive that if they weren't kept at near absolute zero temperatures, their own heat would blind them to the faint signals coming from deep space. The heart of the Webb telescope is its primary mirror. At 21 feet across, it's nearly 3 times wider than Hubble's. This mirror is a mosaic of 28 hexagonal segments, each coated with a microscopic layer of gold to perfectly reflect infrared light. When these segments work together, they create a mirror so flawlessly aligned that it could detect the heat signature of a single bee on the surface of the moon. But this incredible size and sensitivity are only part of the story. The real secret to detecting K2-18b's atmospheric composition lies in Webb's groundbreaking coronagraph technology. Imagine trying to see a tiny firefly next to a blazing searchlight from 1,000 miles away. That's the challenge of studying a planet's atmosphere when its star is billions of times brighter. Webb's coronagraph acts like a precision-engineered cosmic eclipse. It uses a series of microscopic masks and mirrors to block out the blinding glare of a star, allowing the much fainter light from an orbiting planet to pass through. This isn't just a simple disk, it's a complex, multi-layered system that operates with a precision of just a few billionths of a meter. This allows scientists to remove the roar of the star's light so they can hear the whisper of molecules in the planet's atmosphere underneath. The discovery of K2-18b's secrets is not just a triumph of engineering, it's a victory for humanity's unwavering desire to peer into the darkness and find a sign of life. And with this tool, we were able to find the next crucial piece of our cosmic puzzle.
The story of K2-18b and the life it may harbor is a testament to the immense power of its star and the incredible resilience of its atmosphere. But none of it would be known to us without the one tool that made the impossible a reality: the James Webb Space Telescope. Webb is not just an ordinary telescope. It is a technological marvel floating 1,000,000 miles from Earth at a stable gravitational point known as L2. At this location, it exists in a state of perpetual darkness with a massive sun shield the size of a tennis court blocking all light and heat from our star. This allows Webb's instruments to remain colder than the surface of Pluto, a crucial condition for it to function. To understand why this extreme cold is necessary, we must understand the mission of the telescope. While the Hubble Space Telescope gave us stunning visible light images of the cosmos, Webb was built for a different purpose: to see the universe in infrared light. Infrared is invisible to the human eye, but it is the key to detecting life on distant worlds. Everything in the universe, from stars to planets to human bodies, emits infrared light, which we experience as heat. Webb's instruments are so sensitive that if they weren't kept at near absolute zero temperatures, their own heat would blind them to the faint signals coming from deep space. The heart of the Webb telescope is its primary mirror. At 21 feet across, it's nearly 3 times wider than Hubble's. This mirror is a mosaic of 18 hexagonal segments, each coated with a microscopic layer of gold to perfectly reflect infrared light. When these segments work together, they create a mirror so flawlessly aligned
that it could detect the heat signature of a single bee on the surface of the moon. But this incredible size and sensitivity are only part of the story. The real secret to detecting K2-18b's atmospheric composition lies in Webb's groundbreaking coronagraph technology. Imagine trying to see a tiny firefly next to a blazing searchlight from 1,000 miles away. That's the challenge of studying a planet's atmosphere when its star is billions of times brighter. Webb's coronagraph acts like a precision-engineered cosmic eclipse. It uses a series of microscopic masks and mirrors to block out the blinding glare of a star, allowing the much fainter light from an orbiting planet to pass through. This isn't just a simple disk. It's a complex, multi-layered system that operates with a precision of just a few billionths of a meter. This allows scientists to remove the roar of the star's light so they can hear the whisper of molecules in the planet's atmosphere underneath. The discovery of K2-18b's secrets is not just a triumph of engineering. It's a victory for humanity's unwavering desire to peer into the darkness and find a sign of life. And with this tool, we were able to find the next crucial piece of our cosmic puzzle.
The James Webb Space Telescope's incredible technology allowed it to peer through the glare of a distant sun and analyze a planet's atmosphere. But what it found there was far more than just a chemical cocktail. It found a signal that could be the strongest evidence of life we have ever discovered. It's time to talk about the molecule at the heart of this entire mystery, dimethyl sulfide. On Earth, this organosulfur compound is a hallmark of biology. It is produced in enormous quantities by marine life, particularly by phytoplankton, the microscopic organisms at the base of the ocean food chain. When these tiny plants metabolize or die, they release dimethyl sulfide as a byproduct. You've almost certainly smelled it, even if you didn't know it. DMS is a major contributor to that distinct, bracing smell of the sea. Its biological origin is so dominant on our planet that for years, astrobiologists have theorized that its presence on another world would be an unambiguous biosignature, a smoking gun for life. Other potential biosignatures, like oxygen or methane, have non-biological sources. Volcanic activity can release methane, for example, and oxygen can be produced by photochemical reactions in an atmosphere. But until very recently, there were no known natural, non-biological processes that could produce dimethyl sulfide in the quantities detected in K2-18b. Its presence is a puzzle that, for now, can only be solved by life. It is the perfect chemical fingerprint because it is so intimately connected to the metabolic processes of living organisms. While some recent lab studies have explored potential non-biological ways to produce DMS, such as in comets or under very specific atmospheric conditions, none of these models come close to explaining the sheer abundance of the molecule detected in K2-18b's atmosphere. The concentrations found by Webb are thousands of times stronger than what is found in Earth's atmosphere. This suggests that if life is the source, it isn't just a trace amount. It's a vast, global-scale biosphere pumping this gas out at rates that dwarf our own. So, when the James Webb Space Telescope detected the unmistakable infrared signature of dimethyl sulfide in the atmosphere of K2-18b, it wasn't just another data point. It was the moment we found something that for decades we've been searching for, a chemical fingerprint of life that, in the face of all current knowledge, has no other explanation.
In the world of science, certainty is a rare and precious commodity. Scientists don't deal in absolutes. They deal in probabilities, statistical confidence, and margins of error. When a discovery is announced, it's never with a simple, "we found it." It comes with a number, a threshold of proof that must be met to be taken seriously. For particle physicists at CERN, a discovery requires a 5 sigma level of confidence, a monumental 99.9999% certainty. But for the James Webb Space Telescope's discovery of life on K2-18b, the number was equally staggering, a 99.7% statistical confidence. So what does that number actually mean? It's far more than a simple percentage. It represents a 3 sigma detection, a standard of proof that is the bedrock of countless scientific fields, from chemistry to medicine. Imagine a bell curve, the perfect statistical representation of a random set of data. 1 sigma is the range where 68% of the data will fall. 2 sigma captures 95% of the data, and 3 sigma captures an astonishing 99.7% of the data. This means that for the dimethyl sulfide signal from K2-18b, there is only a 0.3% chance that it's a random fluctuation, a fluke, or a ghost in the machine. It means the odds of it being a false alarm are less than 3 in 1,000. To put this into perspective, imagine a manufacturing process that produces 1,000,000 parts. A 3 sigma process will produce only 2,700 defective parts. It's an almost perfect process. For K2-18b, the signal for dimethyl sulfide was so far outside of the expected noise and so powerful that it fell into that incredibly small 3 sigma outlier zone. This isn't just a strong hint, it's a statistical declaration. In the world of exoplanet science, where discoveries are often subtle and require months or years of follow-up to confirm, this level of confidence is unprecedented. It's a statement that says, we've checked everything, we've ruled out every known possibility, and the only explanation left is biological activity. This statistical certainty is the backbone of the entire discovery. It gives the scientific community a firm foundation upon which to build, and it gives all of us the most compelling evidence yet that we are not alone. And it is this certainty that completely changes our perspective on the next crucial piece of our story.
The statistical certainty of the discovery is in itself a historic milestone. But the real significance of K2-18b goes far beyond a single data point. It completely shatters our most fundamental assumptions about life in the universe. For decades, our search for extraterrestrial life was defined by a single Earth-centric idea. We needed to find a planet just like our own. We were looking for an Earth twin, a rocky world orbiting a sun-like star in a temperate zone where liquid water could exist on its surface. This model, while logical, was limiting. It was like looking for a human in a universe filled with every conceivable form of life. K2-18b has proven that this model is obsolete. It shows us that life can emerge and thrive in conditions that we once considered completely inhospitable. The discovery has launched a new field of study in astrobiology focused on what scientists call Hycean worlds, water-rich planets with hydrogen atmospheres. These worlds are not just a theoretical possibility, they are a real and tangible target for our telescopes. This realization is so profound because worlds like K2-18b, super-Earths orbiting red dwarfs, are the most common type of planetary system in our galaxy. If life can emerge on a Hycean world, then the number of potentially habitable planets in our Milky Way could be hundreds of times larger than we ever thought. Suddenly, the universe isn't a vast, empty space where life is a cosmic accident. It's a vast, rich ecosystem where life is the rule, not the exception. This paradigm shift also changes the way we look for life. Instead of just searching for the familiar biosignatures of oxygen and methane, we can now look for what are called agnostic biosignatures, chemical imbalances that can only be explained by life, regardless of what form it takes. The dimethyl sulfide on K2-18b is the perfect example of this. This discovery is more than just a scientific finding. It is a profound philosophical statement. It tells us that life is robust, adaptable, and far more diverse than we could have ever imagined. It tells us that we are not the pinnacle of creation, but one unique path among countless others. It gives us a new lens through which to view the cosmos, a lens that sees not just rocky planets, but a galaxy teeming with diverse and strange worlds, each with its own story to tell. And it forces us to ask the ultimate question: what could life on a world like this actually be like?
The discovery of a Hycean world has forced us to reconsider the very nature of life, but it also gives us a tantalizing opportunity to imagine a completely new kind of biology. We've established the incredible stability of K2-18b, but what does that mean for the life that might inhabit it? What would a world with a hydrogen atmosphere and a vast, deep ocean actually look like? Computer models suggest K2-18b's ocean is not just water. It's a hydrogen-rich solution under immense pressure, with depths that could be hundreds of miles deep, dwarfing all of Earth's oceans combined. This is a planetary ocean, a water universe that provides an immense environment for life to develop. In this environment, life would be fundamentally different. The very atmosphere could be a source of energy. Instead of breathing oxygen, organisms on K2-18b might be hydrogen breathers, metabolizing the abundant hydrogen dissolved in the ocean. This is not science fiction. On Earth, some microbes use hydrogen as an energy source. But on a planet where it's a dominant element, this kind of metabolism could be the basis for an entire, thriving ecosystem. With the planet's immense size and stable conditions, life could have had an almost unlimited amount of time to develop complexity that is beyond our imagination. The ocean could harbor a layered ecosystem, from the pressure-crushed depths to the surface. It could be home to transparent organisms that use hydrogen and methane for energy. The sheer volume of this ocean means that life could be so abundant and so widespread that it's not a struggle for existence, but a flourishing, planet-wide collaboration. The lack of seasons, the stable temperature, and the vast volume of water could allow life to invest its energy into growth, reproduction, and evolution, creating a biosphere of unprecedented complexity. And while we might imagine these creatures, the truth is, the reality is almost certainly stranger. This life would have evolved in a world with 3 times Earth's gravity, under a hydrogen atmosphere, and in an ocean of unimaginable pressure. It might use entirely different biochemical pathways and have a cellular structure that we can't yet conceive of. The life on K2-18b would be a powerful testament to the universe's creativity, a mirror not of ourselves, but of the endless possibilities of biology. In the final part of our journey, we will reflect on what this incredible discovery means for us and what comes next.
We've traveled a great distance in our journey, from the statistical certainty of a single molecule to the grand speculation of a living world. We've seen how the James Webb Space Telescope didn't just discover a new planet, it discovered a new paradigm for life itself. But this is not the end of the story. It is merely the beginning. The discovery of life on K2-18b is the first step in a new era of astrobiology, a systematic and methodical search for life in our cosmic neighborhood. The tools that will take us on the next part of this journey are already being built. On Earth, the extremely large telescope is under construction in Chile's Atacama Desert. With a primary mirror nearly 130 feet across, it will be powerful enough to analyze the atmospheres of nearby planets with unprecedented detail and even detect dozens of new biosignatures. In space, missions like the Habitable Worlds Observatory are being planned to directly image Earth-sized planets around sun-like stars. This next-generation telescope will be specifically designed to hunt for life, taking the groundwork laid by Webb and pushing it to a scale that was once unthinkable. This is a future where the search for life isn't just about waiting for a signal to arrive. It's about actively and systematically searching for the chemical fingerprints of life on a galaxy-wide scale. The discovery of K2-18b will be remembered as the moment humanity officially ended its cosmic loneliness. It is a profound declaration that we are not a fluke, but a part of a cosmic community. We will transition from a species that wonders about life elsewhere to a civilization that knows life exists throughout the galaxy. The universe is not an empty space punctuated by rare pockets of life. It is a vast ecosystem where biology and chemistry dance on a scale that dwarfs anything we have ever imagined. The moment we're no longer alone is almost here, and we have the proof to know that it's not a myth now.
If you're as excited as we are about the truth of the cosmos, then you'll want to see our last video. We explored the incredible reality of a world far stranger than any fiction. A world right here on Earth, hidden beneath the streets of New York City. The link is in the description. To keep exploring mysteries with us, be sure to like this video, subscribe, and let us know what myth you want us to tackle next in the comments. We'll see you in the next video.